Alright, ME627. Today we are going to look at the state space. So let us say we have a system of equations. Q dot is equal to F of QT, written in first order form. This we have discussed. This is the general case. This is called non-autonomous. If Q dot is a function only of Q, then we call this autonomous. There's a difference. The difference can technically be said to be small. For example, if I have Q dot is equal to F of Q and U dot is equal to 1, this combined system is technically autonomous. But you see, it is the same as that system. This is the same as that system. However, there is a difference, and as we go through the semester you will see that that difference will become clearer. Okay, now let us look at this system. This is a very important class of systems. We will study forcing later. Now this vector Q, let us say Q is equal to Q1, Q2 and so on up to Qn. So this is an n-dimensional system. Imagine that we could draw a graph of it. In 2 it is easy, in 3 it is, we can sort of pretend to draw it in 3. But let us say this is Q1, let us say this is Q2, let us say it is Q3, and maybe there are others that we are not able to draw, so temporarily we will just draw 3. So think of this n as tentatively 3 for purposes of illustration. Very good. Now let Q be some value. That value, whatever at some time, is a point in this space. As time changes and Q evolves, this point keeps moving. So it traces out some kind of curve in this space. This space is called the state space. This point represents the state. The differential equation, whether this or this, gives you a rule for how this point moves around in this state space. This path is called a trajectory. In this path, the time variation is suppressed. Time. Okay, so let me explain what I mean by time variation being suppressed using a separate example. Of a parametric plot. Let us say x is equal to cos t, y is equal to sin t. T is a parameter. This has a parametric plot. That parametric plot is a circle of radius 1. This is t equals 0, this happens to be t equals pi by 2 and so on. It traverses this path, but basically over here this set of parametric equations generates that curve. Now I come along and I say I have a different one. I have x is equal to cos of t square and y is equal to sine of t square. Well, it traces out the same circle. It just goes round faster and faster. It goes at a non-constant speed. Right? So this one and this one are very different functions of time, but it doesn't matter. The path traced is the same. Now if you go back to this curve, you will see that the time history is suppressed. But when the time history is suppressed, what happens is instead of looking at this function of x, y and t, instead of looking at x, y and t, we are just looking at x and y in some sense. We are just looking at q. So the advantage is that dimension is decreased by 1. But there's more. For example, this is a more geometrical view, right? So for example, if I have a periodic function, if I have a periodic solution, then the periodic solution will, over here it will look like a closed curve. So that's a periodic solution. Over here, if I have several solutions that go to the same point, then that is actually a stable equilibrium solution, right? And so in this way we are able to talk about these things. This is a stable equilibrium. We are able to talk about these things, this one and this one here, in a geometrical view without finding the exact temperature dependence, right? So the time variation is suppressed. Okay, so this is one reason why looking at the state space and the phase space, which we will come to soon enough, is important. Okay, but when we try to understand the behavior in state space, so what happens is we may do something like, it's also called phase space. Okay, so let us take this system, x double dot plus x equals 0. We will write it in first order form. So we will write x dot is equal to v dot is equal to minus x. You know these are sinusoidal solutions. Every solution is sinusoidal. What we will do here is that state space or that phase space, which we call here, this is the v-axis, this is the x-axis. Suppose I start here. What happens? X dot is v, x dot is 0 because v is 0. V dot is minus x, so v dot is negative. What does that mean? That means it is going down vertically. So basically it will go down like this and it will give you a circle. That's one solution. This part will have a vertical tangent here. Here is another solution. Here is an equilibrium. Here is another solution. This gap should be bigger. I can try to fix that here. Okay, all solutions. Periodic. Okay, closed curves. Now here's the interesting thing. What happens if I have x double dot plus x plus x cube equals 0. Well, interestingly, all solutions are still closed curves. They may not be perfectly circular for larger amplitudes, that is a different matter. Right? So we have this geometrical view now. Let's take another example. What about x double dot plus some 0.1 x dot plus x cube equals 0. Now over here I know that this is the oscillatory part. It's like a nonlinear spring term from a mechanical analogy. This is like damping, so all solutions are damped, and so I expect that solutions look like this. They look like this. Okay, so that's the phase portrait. Okay, enough trajectories shown so that the collective behavior of all solutions is clear. This is a very nice way of thinking about things. 2D it works really well, 3D it works less well, but it still works, and beyond that we don't know how to draw. That's a different matter. But the idea that there is something like this can help us sometimes in our analysis. Okay, so sometimes we may be interested in a lower dimensional subset of all solutions, and those we may be able to draw and things like that. So it's nice to understand that there is something called a phase space, or that state space in this dynamical systems context is called a phase space, and then there is an n-dimensional phase portrait that shows all trajectories. So now how do we start thinking about a phase portrait? We can't just take some system and autonomous. Okay. If it was not autonomous, then you would have to be technically drawing the other direction. So for example, let's do this one also. So let's do this one first. So what you have is, let us say I'll do 2D. So maybe you have solutions that look like this. They are going to a fixed point over here. Another solution coming like this. Oh, that didn't work out so well. Let me connect it to this one. Okay, and then there are other solutions that are going in like this and so on. So this is how it is for the autonomous case, 2D. But when I come to let's say this one, when I green maybe, so then what I will do is I will have so this will be Q1, this will be Q2, and this will be T. And actually I don't have a fixed plane now, so I may have a trajectory and it goes around and comes like this, and and reaches an equilibrium in this way. So when I am looking at it a long time, that may be the solution. When I am looking at this same solution here, because I am removing the variation due to time, then I am able to see this, but the journey from here to here is possible only for the autonomous case. For the non-autonomous case, we cannot do this, and the reason we cannot do this is that over here, uniqueness of solution says that I cannot have two arrows like this. From here, if this is the condition, initial condition, if it evolves like this, that's what it does for the autonomous case. However, for the non-autonomous case, at some instant, some value of t, it may be going like this, at some other value of t, it may be going like this. In this way, trajectories will intersect if I don't show the t variation. When I show the t variation, then the trajectories will not intersect. Okay, so for this reason, we will think about autonomous systems with fair amount of care. These are some of the differences. So now when we think about autonomous systems, what we will do is we have q dot is equal to f of q. One way to start is to say, are there values q star such that f of q star equals 0? If there are, now I'll do this in 2D just for simplicity. So let's say here is 1 and here is 1. Okay, so then these are equilibria. I can do a local analysis. I can do a local analysis for this region, and I can do a local analysis for this region, and then I have to stitch things together, patch things together for the overall picture. Who knows how it will be? We will have to see. Okay, so there may be another equilibrium here and whatever it is. So we will have to see those. So there are various things that we will study in this situation. So we will start like this. So we will seek equilibria and then we will look for local analysis. Okay, with that motivation, let us come here and say q dot is equal to f of q, and let there be a q star such that f of q star equals 0. Then we will write what we call a variational equation. Okay, so what we say is let q be equal to q star plus xi, with the understanding for local analysis xi, the magnitude is small. Okay, q star is fixed, not a function of time, so therefore q dot is equal to xi dot is equal to f of q star plus xi is equal to f of q star plus a Jacobian matrix. Higher order terms, which we will neglect. Okay, this part is 0. This we are neglecting. This is exactly 0. That leaves this. This is a matrix. What is this matrix? This matrix is del f1 del q1 del f1 del q2 and so on, and then over here del f2 del q1 and so on, and this whole thing evaluated at q star. Let me give you examples. Okay, let us say x double dot is equal to x minus x square. So, yay, nonlinear system. Okay, I'm sure you are very excited. Alright, so we will say x dot is equal to v dot is equal to x minus x square. This is our system in first order form. Think of this as Q1, think of this as Q2. Alright, for this to be 0, clearly v has to be equal to 0, there is no doubt about that. X minus x square equal to 0 means x times 1 minus x equal to 0 means x equals 0 or 1, x equals 1. So we come here, we will draw our phase portrait here, and you see this is v, this is x, and this is one equilibrium and this is another equilibrium. Okay, alright. Let's come to the equilibrium at 0, 0. Then the Jacobian matrix is del f1 del x1, that is 0, del f1 del x2, which is v, so that is 1, del f2 del x1, or that's 1, well, it's 1 minus 2x, but x is 0, so that's 1. And then del v is 0, so it's 0. Okay, very good. This is the linearization. So what we will have here is xi dot is equal to this times xi. Okay, very good. Let us move here so that I can analyze this system comfortably. Let us look at its eigenvalues. Okay, so well, maybe I won't do that yet. What I'll do is I will point out that when it's simplest to treat for the moment. I will do this with greater care later, but for the moment it is simplest to realize that for x equals 0, this is just x double dot equals x. This is like an inverted pendulum. There is the characteristic equation is r square equals 1, r is equal to plus minus 1, and actually there is basically one unstable eigenvector, one eigenvector for unstable solutions and one eigenvector for stable solutions. How do I know these directions? Because they are 1 and 1 over here, but you can try it out, you will see that it is correct. But how do I know the directions also? Because when v is positive, then x increases. If v dot is rx, right, and r is 1, then this is the unstable part. Alright, let's come here and do a linearization around 1. So once again, the first row does not change, 0 and 1. Over here the derivative is 1 minus 2x. For x equals 1, that is minus 1 and 0. Okay, so xi dot is equal to this one xi. Okay, now once again I will do this more formally later, but I'll just take a small shortcut here. I'll say xi1 dot is equal to xi2, right? Yes, and xi2 dot is equal to minus xi1. Therefore xi2 dot is equal to minus 1 xi dot is equal to minus xi2. So you see it is sinusoidal. You can see that. So over here, this equilibrium, or near this, it is like an oscillator. This much we got from local analysis. Okay, now from experience or a little bit of thought or a little bit of faith or a little bit of numerical simulation, you will realize that this solution actually continues and comes back here. So over here there are oscillatory solutions where the nonlinearity is significant. There is an oscillatory solution here whose time period can be quite large. Sorry, this pen is a problem. Please excuse my poor picture. Over here there are solutions that go like this. They go off to infinity. This one comes from somewhere. This one comes like this, goes around and goes off to infinity, and that's the phase portrait of this system. So for example, if you want bounded solutions, then you want your initial condition to lie inside this region. Those are the bounded solutions, right? What happens when this system has some added damping, things like that, we will study later. So over here, for example, if I put minus 0.1 x dot, then this part here, which I will now make, this part would not change much, but over here they would be spiraling in. Let me make the brush a bit bigger so that you understand what I am saying. Over here it will be spiraling in. So then it will change, and you can sort of think about that phase portrait also for in your spare time, but also in later lectures. This leads us to this fundamental issue of xi dot equals, let us say, a xi. A is a constant n by n matrix. If we don't understand this, then we can't draw anything near the equilibria, and we are not really qualified to think of phase portraits. We are not qualified to think of nonlinear systems. So to think about nonlinear systems, we have to understand the simplest possible case first, which is the linear constant coefficient system, also known as the linear time invariant system. The solutions are definitely time varying. The time invariant refers to this part. The parameters in the system are independent of time. Okay, so how does the solution of this begin? You may remember that we have to look at solutions of the form xi equals u e to the lambda t. Okay, so when we do that, then we get lambda u e to the lambda t equals a u e to the power lambda t, but e to the power lambda t is not 0, you see, so we can cancel that, and we are left with a u equals lambda u. And so we know that we have to look for the eigenvalues of a. We go for determinant of a minus lambda I, set it equal to 0. There are n roots including multiplicities. Okay, you know that. And then this is just a review of linear systems, and these n roots with multiplicities, we don't care too much about the multiplicities for two kinds of roots. So roots, these eigenvalues are of three kinds: real part greater than 0. These lead to exponential growth. Real part less than 0. These lead to decay. Real part equal to 0. these require further analysis. Additionally, over here, if we have imaginary part not equal to 0 for any of these, then we have oscillations. And therefore you will understand that a lot of this course is going to be interested in real part 0, imaginary part not 0, and requiring further analysis. Okay, let us stop here for today.